Equilibrium review questions. We'll have a look at a few, and then I'll give you a question for you to try on your own at the very end of the video like we always do. But I also want to make it very clear, based on what we've been going through so far in our videos for equilibrium. Okay, we've looked at the temporary equilibrium constant, we've looked at KEQ as well. Okay, remember this KEQ was the permanent equilibrium constant, and we also deemed this as the ratio between the concentration of the products, right, and the concentration of the reactants. And I just put it in a big bracket here. This was the general term for the equilibrium constant, right? And when you determine equilibrium constant, it tells us where it's going to shift. So this KEQ here is kind of a blanket, general, overarching term. Why am I focusing so much on KEQ? Because we've also branched out into KP, right? But we haven't talked much about KC. What the heck, right? Well, you've actually already know what KC is, even though we haven't set it at face value. KC, okay, again, it is the activities of the reactants and the products, right? Because it is under the subheading of KEQ, but it can be expressed only for molarities. Okay, so when we deal with things like moles per liter, okay, obviously this we're dealing with molarity, so you'd be using Kc as our equilibrium constant. For Kp, you're already quite familiar with this. For Kp, this is obviously for partial pressure. So this is obviously when we're dealing with gases, right? It's better to use this when dealing with gases, okay? So then we will be using Kp. So as you go throughout this equilibrium review questions, if you notice or spot Kc in the question, it's nothing different than what you've been learning so far. It's just specifically the variable for molarities. We obviously have moles for our H2 and for our N2, and they are in a 2-liter reaction vessel. So obviously we know our formula for concentration. We have both of them. Okay, we have the moles and the volume. So of course for the concentration of our first reactant, we'll do H2 then, okay, is going to be 1 mole over 2 liters. Okay, so that's obviously just 0.5 moles per liter. We'll do the same thing for N2. Obviously it should be the same value, right? 1 over 2, so it's the same thing. You have 0.5 moles over a liter. What else do we have going on? Well, we don't know what the concentration of NH3 would be, so we're just going to leave that as, you know, as 0 because that hasn't been produced yet. What else is happening in the question? Well, it says that the temperature, okay, 24% of the hydrogen is consumed, okay? So they are giving us some hints of what is happening initially and what has changed. So we have to figure out what happened at equilibrium, okay? Because it got consumed, we got to figure it out. So this sounds like a nice table for us, right? We have our initial, some change is going on, and that resulted in 24% of it being consumed, and of course there's going to be some sort of equilibrium that happened after that. So again, we have all 3 factors. We have the I, we have the C, and we have the E. We definitely got to create the ICE table. So let's write it out. So let's put I, C, E. And we have our N2, we have our H2, and we have our NH3. Let's put all of this in moles per liter. And in terms of our initials, oops, this was 0 here. Okay, in terms of our initial concentrations, we had 0.5 moles per liter. For N2, we also had 0.5, and then for NH3, we had 0. In terms of our changes, for N2, there was only one coefficient, so it would just be negative x. For H2, it would just be negative 3x. And then for our NH3, it would be plus 2x. So let's add them all up and sum it for our E's. There we have it. Now we realized at temperature 24% of the hydrogen was consumed. So let's just look at the hydrogen section here. 24% of it. Okay, so we started initially with 0.5%, but then 24% of it got consumed. So that 24%, we gotta be putting it over here. Okay, so we can kind of just scratch that out. Okay, what is the 24% of 0.5? We end up getting 0.12 or 0.12. So I'm just gonna write that over here. Okay, now that we've written that, what is the equilibrium constant for this reaction? So we got to put our Kc is equal to, obviously our NH3, our product's got to be on the top, so we'll have our NH3. It's got to be to the power of 2, all divided by our first reactant here, our N2, okay? And our N2 over there is going to be to the power of 1, and then for H2, it's going to be to the power of 3. Now, we have to fill and substitute these variables with some values. Well, we got to figure out what x is first. Well, we could easily find out x by doing this, right? Because we know that this 0.5 minus 3x gives us 0.12. So I could simply just do some algebra here and just isolate for x, right? So we're going to have negative 3x. 0.12 minus 0.5 gives you negative 0.38. Okay, so then you would just isolate for x. That gives you 1266. So I would just have to substitute this x value into here and into there. Okay, so we'll do this as we go along. For our NH3, right over here, it's 2 multiplied by this x value. So what do you add? What do you get? I end up getting 0.2532. Okay, this is going to be squared. How about for my N2? Okay, where is my N2? It's over here. So what is 0.5 minus this x? 0.3734. Okay, that's all the way to the power of 1. And then for our H2, our 0.12 here, we can just leave it the way it is, and it's to the 3. Your little calculation, what do you end up getting? 99.36. That is your answer. 3-liter reaction vessel contains 3.6 moles of iron 2 bromide, so that's this one over here. 1.2 moles of iron 3 bromide, so this one over here. And then 2.1 moles of bromine gas. Okay, so obviously these 2s and 3s over here, these Roman numerals, can be a little bit not so pleasing to the eye. So we can actually just write this 1.2 moles. It's going to be right around here. I'm just going to put that in there. And then for the 3.6 moles of iron 2 bromide, I'll just put it up here. Okay, and remember all of these are divided by 3 liters, okay, based on our C is equal to N over V formula. So in terms of our concentrations, let's write it in. For the concentration of our FeBr3, so our iron 3 bromide, what do you end up getting? 1.2 divided by 3, 0.4. And then for our, this is again moles per liter, for our FeBr2 iron 2 bromide, what do you end up getting? 3.6 divided by 3, 1.2. And lastly for our bromine gas, okay, our 2.1 divided by 3, end up getting 0.7 moles per liter. We have our concentrations. Is the system at equilibrium? Well, in order for us to figure out if it's at equilibrium or not, we have to know what variable to use. It's quite obvious we have to use QEQ. Why? Because we have the KEQ already, right? The KC, remember KEQ is KC, okay? That's just the heading for the KC. Well, you know that we're dealing with molarity right now, so that KEQ is clothed under KC, okay? And we already know that it's at 0.98, which means we have to find our reaction quotient. Once we find a reaction quotient, we can gauge and compare it with the 0.98 and see if it's greater than Kc or if it's less than Kc. So let's put our KEQ and let's start putting things together. We're going to be putting our products. our products on the very top are going to be these two. So it's going to be 0.4. Okay, and how else we have it to the power of 2 based on what's written over there. Oh, sorry, not 0.4. This is FeBr2, so that's 1.2. So you see how it's very important to write it on the side before you plug it in, otherwise it could be a little confusing, right? So we got 1.2 to the power of 2 multiplied by our Br2, which is 0.7. Obviously this is to the power of 1, there's only one coefficient. Then this is all divided by our 2 FeBr3, so that's this one over here. And of course this one has to be to the power of 2 as well. What do you end up getting? You end up getting 6.3. So we just compare this 6.3 value with what we see up there. Okay, obviously our 6.3 is larger than our KEQ. Our KC gives us 0.98, right? So our KEQ, branded as KC for this kind of question, because we're dealing with molarity, is just 0.98. So of course this QEQ is much larger than the KEQ. This QEQ is greater than the KEQ. What does this mean? This means that the products are greater amounts. If it is greater, is the system at equilibrium? Absolutely not. So then what does this mean? This means that the products are in greater amounts, and therefore it will shift to the left. Okay, and it's obviously going to shift to the left to alleviate that stress based on Le Chatelier's principle. It's going to go towards the reactant formation. That's the answer. In an experiment, 2 moles of HI are introduced into an evacuated 10-liter container. Calculate the concentration and number of moles of each substance at equilibrium. Okay, we have to use our C's with the N over V. For our moles, we got 2 for our HI. Let's write it out. Divided by 10 liters. This gives us 0.2 moles per liter. And this, of course, this is for the HI. Now we don't know anything else because, of course, our products are going to start off at 0. Now let's write in a little ice table. I'm going to put our our first reactant on the left side. Then we'll have our products over here. So for our HI, it's going to be 0.2. Again, just disclaim that these are all moles per liter. For our H2, we don't know. For our I2, we don't know. In terms of our change, we can tell that this one here is a negative 2x. This one here is a plus x. This one here is also a plus x. Let's sum them up for the equilibrium. Now that we've done this, we understand that the Kc that they give us is 0.0156. So we'll just plug it into our little expression formula here, right? K is equal to the products over the reactants. So we're putting in what we need for the products on the top, our H2. So for our H2, again, it's going to be just to the power of 1. I2 is also going to be to the power of 1. For our products, it's just going to be to the power of 2. Bring this over here. So we're going to get our 0.0156, and then our products over here, we're going to start with our x multiplied by our other product, or the x, and then on the bottom for our reactant is going to be 0.2 minus 2x. Also, do not forget that this has an exponent of 1, this has an exponent of 1, and this has an exponent of 2. So, putting these together with the exponent rule, those exponents add up, so you get x squared. On the bottom here, we keep it the same. And then from here, we can square root. Square root this, square root this, square root this. We've got an easy, perfect square. In terms of this value, it would be 0.1248. All over 0.2 minus 2x. From here, just cross multiply. So we've got our x over here, our 0.1248, multiplied by our 0.2 minus 2x. X is equal to 0.02497 negative 0.2496x. And then from there, add them up. Isolate for x. We're getting 0.019982. So this is my x value. What are we going to be doing now? Well, we're going to plug them back in to our chart over here. So for the concentration of, so again, we're at equilibrium right now, okay? The concentration for my HI is going to be inserting this x value within here. So we get our 0.2 minus 2 multiplied by 0.019982. Okay, and then that would give us 0.16. It's going to be moles per liter. For my H2, that doesn't change. That's going to be given 0.011982. And then, of course, for my I2, also the same. Now, these are all in concentration. The question does ask it for moles as well. So as long as you just multiply by whatever the liters was, so you've got 10 liters over here, 10 liters over here, 10 liters over here. Obviously, this liters cancels out, this liters, and this liters cancels out. So you end up getting, for the amount of moles for our HI, we get 1.6 moles. For my HI, 0.199 moles for H2, and also same thing, 0.199 moles for H2. This is your answer. Alright, have a look over here. This is our green question of the day. Please give this one a try. Just before you attempt this, if you're confused about this L to the -1 here, I would highly suggest you see the video link in the description for the units to calculate the rate law practice questions. So I'm going to be putting those two video links in the description for you to decipher what this -1 represents. Once you watch those videos, you should have a better understanding of how to grasp what this means in this question, so that it does not psych you out when you answer a question that deals with these kind of units, okay, that are presented in front of you. Again, look at that video if need be prior to answering this question, and I'll be giving you the answers shortly. This is the answer.